So the next concept I want to get into is control limits. Control limits are the upper and lower boundaries for acceptable samples. Control limits are calculated from the sample data. Control limits are used on weight sheets to help determine if the process is in control. Our process is considered in control if no more than 3 out of every 1,000 samples are outside of the control limits. So I have my target weight, right? And the control limits would be above and below that target line if I'm looking at the actual weights. I don't want any more than 3 out of every 1,000 samples I take to be above or below those lines. Now I can't just say, oh, that's easy. I'm going to make the lines wider. I'm going to move the top line up and the bottom line down. And now I won't have any outside of the limits. But it doesn't work that way. These are mathematically calculated lines. You don't just draw them in. They are calculated based on the capabilities or the history of your process. So if I've got a machine that bags 1 pound bags of salad, then I need some data. I need to gather some sample data for how does this process work? How does this process go? How close to that 1 pound can I get consistently? And based on what is considered a good, stable, effective operation of that machine, I calculate my upper and lower control limits. Now, you don't have to worry about how to calculate them, but these control limits are very important. So the control limits, there's upper and lower control limits. And there's one other that I'll get to in a minute, but the control limits are one very important concept in monitoring statistical process control. We also need to know what the heck is in control versus capable. Now, this slide was not in the training. I added this slide for the class. And the reason I added it is because this concept is one that I think is more likely to cause confusion in some of the laborers that are in the quality control that are learning the process. And this training is intended to give them the tools they need to do their job. If they show promise to move up, we can give them additional training. But you in this class need to understand the idea of in control versus capable. A process is in control if it is producing a product that has a stable mean and variation over time. In other words, the process is producing a consistent product. So let's say I go back to the bagged salads. I'm making 1 pound bagged salads plus or minus a half an ounce. And I show that my machines, my operating, the way I'm running it with the products I'm running, that is something that this machine can do. That is in control. It's stable. It's 1 pound plus or minus a half of an ounce. A process is capable if it's able to meet the specifications of the customer and the legal limits required for the product. What if I needed a 1 pound bag of salad plus or minus 1/10 of an ounce, not a half an ounce, but 1/10 of an ounce? That's not what my machine does. My machine doesn't make bags of salad at 1 pound plus or minus 1/10 of an ounce. It produces bags at 1 pound plus or minus a half an ounce. So my machine isn't capable of being that accurate. And that's an important difference. It doesn't mean if I can't do what the customer is asking me to do that I'm out of control. It just means I need a more sophisticated set of machinery that can be that much more precise. Let me give you a second example. Let's say I'm making ball bearings, and the ball bearings that I'm making, my machine is capable of making ball bearings to within 1/1000th of an inch. Great. As long as I can keep making ball bearings that meet the right specifications, or not, excuse me, scratch that. If I can keep making ball bearings that are stable plus or minus 1/1000th of an inch, my process is in control. But what if my customer says, hey, I want ball bearings that are plus or minus 2/1000ths of an inch. I don't need them that accurate. Fine. My process is capable. I can make them within 1/1000th of an inch. They only need them within 2/1000ths. My process is capable. I can make them ball bearings if we can agree on a price. But what if another customer comes in and says, I need them to be with plus or minus 1/10,000th of an inch. I need those ball bearings to be really, really accurate, really precise. Then my process is incapable. My process can make ball bearings consistently in control plus or minus 1/1000th of an inch. It is not capable of making ball bearings plus or minus 1/10,000th of an inch. Or maybe it is with some minor updates. Maybe I can update my machinery or slow the machines down, or maybe there's something I can do to meet that customer specifications. Maybe there's not. But again, the control limits are based on what your machine does. The control limits don't give a dang about what your customer's specifications are or what your customer wants. The control limits are solely based on, is your machinery making a consistent product? And then it's up to you to decide if your machinery is capable of producing something that your customer wants, or if you need to upgrade your system to make it more capable. But in control just means it's stable. Capable means it is able to meet the specs of your customer. And the reason I didn't bother with this slide is because McCormick's not going to have an incapable machine. Of course, they're going to have you working on machines that are capable of producing the products that their customers want to buy. That's not a question. But in manufacturing, that is an important distinction. In control just means the process is stable, but it might not meet what your customer wants. If it can meet what your customer wants, it's capable. If it is not able to meet what your customer wants in terms of variation, then it is considered incapable. So before you even start with SPC and start worrying about upper and lower control limits, you need a manufacturing process that is capable of meeting the requirements of your customers. Okay? Very important distinction. Sampling, the next topic. To properly estimate variation, the Quality Assurance Department requires that 5 random bottles are measured per check. So this is a bottle of spices line. That's the training group we were dealing with. There are other things, the bowl packs and bags and things like that. But in the bottling line where we were training, they do 5 random bottles per check. And there was a machine in their facility called Datamite. Lines that did not have the Datamite samples were collected every 30 minutes. Lines that did have the Datamite samples were collected every 20 minutes. Datamite was faster. It's a machine that did the SPC mathematics for you. So it was quicker, and so we could do these faster. But Datamite's not cheap. But if you had the Datamite in place, 20 minutes. If you didn't have it, 30 minutes. That's just the routine that McCormick went through. So if everything immediately went bad right after you did a check, no more than 30 minutes of production could be out of specifications or out of control. So weight control charts are tools. They're just basically a paper form used to monitor and reduce variability in our processes. Samples are collected, plotted at periodic intervals using 2 very simple charts. The X bar chart, X bar is the symbol for an average, and X with a bar over the top is an average or mean. So this is the X bar chart or the mean chart. It has the target, what's the weight you were trying to fill, the upper control limit and the lower control limit. Again, those are based on the mathematical calculations based on historical runs of the same product. The R chart is called the range chart. So what's the range from the lowest to the highest weight in that sample of 5 bottles that you grab to test? So you grab 5 bottles, you get the average weight for those 5 bottles, and you get the difference by subtracting the lowest weight from the highest weight. What's the range or the distance between the smallest to the lowest, or smallest to highest? Upper control limit only, because when you're talking about a distance, you know, the heaviest and the lightest, and you subtract the 2, you're always going to get a positive number. There's no negative number. You can't be below 0. If they were all exactly 1 ounce, 1.00, 1.00, 1.00, all 5 of them 1.00, then the range is 0. There's no distance between them. The high is 0, or the high is 1.0, the low is 1.0. You subtract the 2, you get 0. Okay, you never can get a negative number in a range chart. So let's look at a sample here. Oop, wait a minute. I'll get to a sample in a moment. I forgot. We handed things out in the training. My bad. Actually, let me go to the next slide and just show you the chart so you know what we're talking about. So here are the samplings every 30 minutes. So each of these columns represents a set of samples. And you can see here, 1, 2, 3, 4, 5. These are the 5 bottles that were weighed. And you can see the weights are written in by hand on this old-fashioned chart. It would be punched into a machine, a computer console, or possibly a tablet with an app today. So you've got the time, the weights of the bottles, the total weight, the average. You take the total divided by 5, you get the average. And then the range, where you take the high, the biggest weight, minus the low, the lowest weight. And you get your range. All right. So the average and the range, these 2 at the bottom of each column, are the numbers that we plot. And so here is the average. There it is. It's close, but it is inside of the control limits here in red. So here's the target in the middle. I don't know if it looks a color to you, but I believe it was originally just black. It could have had a green line put on it, but red was always done for the upper and lower control limits. So the average was 37.5, bingo right there. And then the range 1.8 right there. And there's an upper control limit. If you have any more than 5-gram difference between the high and the low, that's a problem. So that's what the X bar chart or the mean chart and the R chart or the range chart at the bottom, that's what they look like. So let's go back. Conditions for action points. There are 4 different conditions for an action point. An action point is when the quality assurance team says, we got to step in and do something. We need to take action. There is either a problem or a potential problem about to happen. And you want to catch it before it gets too far. So if there's any data point outside of a control limit, that's an action point. Does it mean that there's a problem? Not necessarily. What did I say earlier? That you would have no more than 3 out of 1,000 samples. All right. That's not very often. That's days and days and days of samples with none of them outside. So when you get one outside, that's a red flag. Be on your guard, double check your machinery, warn the operator, take a look. Is there a problem? Then there's a shift, a trend, or a MAV violation. Rather than describing a shift and a trend, I will let the next slides describe that for you. MAV violation is the maximum allowable variation violation, and that's when you have stepped outside of the legal limit. And for something like spices, the only MAV violation is underweight. They're not going to violate you for putting too much in. As a matter of fact, there are times when you intentionally put too much in. And let me give you an example before I move on. Why would I give somebody intentionally too much spice? So imagine my 1-ounce bottle of oregano that we've been talking about. And with normal oregano that I get from my normal vendor, it fills it up. Let's say it fills it up about 2/3 full. And I get oregano from a new vendor. And this oregano is very dense, heavy. And so when I put 1 ounce in that bottle, it only fills it up halfway. It looks like I'm cheating the customer. Even though I've got 1 ounce in there, maybe even a little over 1 ounce, the customer might be unhappy because it looks like it's underfilled. And so they have at McCormick something called a minimum fill line. And some products have it, some products don't. But the minimum fill line, I don't care what the weight is. You either fill to the weight or you keep going until you reach the minimum fill line. And so you have to figure out what the new weight is. Instead of giving 1 ounce, we're going to have to give 1.5 ounces to keep the customers happy. And you know when that's happening, if you've got good buyers, your buyer's going to see that you've got really dense product. It's not something that you like getting from your vendor. And so you tell them, hey, we're going to take a hit on this. We're going to have to give a bunch of this away because this product doesn't meet our normal specs. It's too dense. In order to use it in our bottles, we're going to have to give away 1.5 ounces. And so we're not going to pay you as much for it. Now, if it's really, really quality, high-priced oregano, maybe we'll buy it and put it in a special custom high-end bottle. I haven't heard of that for oregano, but there are other spices that do have that situation. A very prized variety is custom packed in a much pricier bottle. But for normal purposes, you've got the minimum fill line. But MAV violations, you definitely don't want to give too little, because now you're violating the law in terms of proper trade, business law. So here's an out of control chart, the one I showed you. I didn't point out the reason that this sample was here. It is out of control because it has points outside of the control limits. In this case, I've got 1 out of control, 2 out of control, 3 out of control. Now this is made up. This would have been a bad day to have 3 samples on the same day, the same line with out of control. But here you can see it was out of control because we're getting overfill. We're giving product away. Here it was out of control because it's under and possibly a MAV violation. And here it's because the distance between the highest weight and the lowest weight was too great. It was over 5 grams. It was actually 7.4 grams and or 6 grams. I guess the line is at 6. I don't know. It's been a long time since I used these charts. But any of these, we've got too much variation in the individual bottles. We got too little product. We got too much product. Immediately, when you see one of these at that shift, it would have been quality control, quality assurance going, we got a problem. Let's make sure we double check everything so this doesn't continue. All right. This particular day looks like a disaster to me. A shift. I did not describe that to you before because I wanted you to see it in an actual control chart. Oh yeah, here you can see the green. A shift is 3 consecutive points all below the target line. Now, technically, it could be above the target line as well, but for McCormick, they didn't worry about 3 consecutive points above because those are not going to be a legal issue. If you have 3 consecutive points above, we'll live with it as long as it doesn't go too far, as long as it doesn't end up being an upper control limit issue. But 3 below, now we're at risk of creating a run where the average weight is below our target fill. This could be a problem. So again, 3 consecutive points all below the target line are a shift. In other manufacturing facilities, depending on what they're making, a shift would also include, in many cases, 3 above. Okay. Does this mean there's something drastically wrong with the process? No. It's a warning. It is a heads up. This could be a problem. But now with this, if we're not using Datamite, we've taken this and it's been below. And now we got another 30 minutes and it's below. Another 30 minutes and it's below. We're now at an hour and a half of potential product. We got to make sure that we don't have the entire run below weight. Now keep in mind there's a little bit of cushion because the target fill weight is a slightly above the label weight. So there's a little bit of room for cushion. And each company has to decide how much above the label weight is our ideal sweet spot to put our target fill weight. So a trend is defined as a set of points, a set of 5 points forming an upward or downward slope. Up, 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 up. So there's 5 points. And they don't have to be a straight line. One could go up a lot and one could go up very little. As long as they continually go up, even though they might not be in a straight line like they're showing here, they don't have to be straight. Just this one's a little higher average, this one's a little higher average. That's saying there's a trend that might be a problem. Is there something going on with our raw product? Is there something going on with our packing machinery, our scales, whatever? What's going on? And you want to explain this. It could be just a fluke. You run these machines long enough, and every one of these is going to happen. Even if everything's running perfectly, no problems whatsoever. Occasionally, you're going to get an out of control above or below the X bar chart control limits. Every once in a while, you're going to get an above the R chart out of control. You're going to get a shift. You're going to get a trend just by random chance. But they are warnings that you should, head up, eyes open, inspect your raw product, inspect your machinery settings, inspect everything to make sure that something isn't going wrong. Now, we don't get into exactly what to do with the people that we're training here. It depends on your machinery. It depends on the rules set by the company, but this would be various tasks would be performed by the quality assurance team or the machine operators to make sure that they respond appropriately when there is a problem with some sort of out of control situation. Again, out of control doesn't necessarily mean there is a confirmed problem. It's a warning. The only confirmed problem is a MAV violation. And then you've got a problem. So here's MAV violation. Any point above the upper control limit in the R chart or below the lower control limit is considered a MAV violation because now you've got too much weight difference. That should not happen. And you've got a low weight. That's when you're at risk of having a legal MAV violation. Okay, so anyway, you can define a MAV violation slightly differently, but that's how they were defined at McCormick. Maximum allowable variation values are dictated by the National Institute of Standards and Technology. These values are set according to label weight per each item code. An example, if the label weight is 80 grams and the MAV is 5, so a weight of 75 grams or below will trigger a MAV violation. Now again, the bar charts, the X bar charts, upper and lower control limits are set by mathematical history of the process, not by MAV settings. So it's possible to have a stable system that constantly gives you MAV violations. Let's say you've got a fill machine and the X bar chart is exactly like you see here, but the MAV violation is right here at this black line above the lower control limit. So what if that is the legal limit? If that's the legal limit, what do you have? A process that is not capable. Not that it's out of control. If it can't meet the maximum allowable variation stably, then sorry, you've got a process that's not capable. You need to fix, redesign, or upgrade your machines because they are not capable of meeting MAV limits for legal business law. When you label something with a weight, you got to meet that weight. So the assumption is McCormick is running machinery that is at specifications that is meeting MAV violation, well within MAV violation limits. And so that's why they can say any point below the lower control limit on the X bar chart or above the upper control limit or the only control limit on the R chart would indicate a potential MAV violation. Have you broken the legal limits with these? You're not certain just looking at the charts. There's a little more to it than this, but from the standpoint of quality control, yeah, this is close enough This is a huge red flag. We are risking breaking the law and selling something underweight when we have these situations. Or we're risking breaking the law by selling things that are so highly variable that one customer buys a bottle and it's got plenty, another customer buys a bottle and it's got way too little. That's not okay. Okay. If proper corrective action is taken for an out of control condition, quality assurance does not need to be contacted. For example, an out of control shift or trend. For MAV violations, quality assurance should be contacted immediately to prevent any finished goods at or below MAV being shipped to our customers. So again, those are their rules. You don't have to memorize that slide right here for the test, but it certainly is important to know who responds, who does what. Quality assurance team members are looking at raw product coming in. They're looking at sampling. The quality assurance lead, who they're talking about here, the quality assurance shift lead person has to be notified if there's any potential MAV violation. But some of these other out of control, if they're minor and they don't look like they're a MAV problem, the technician and machine operator have the tools, the training to deal with it on their own. Regulations from the NIST: no samples at or below the low MAV are allowed to be shipped to customers. The average of the lot must be at or above the label weight. Shouldn't say should, it should be must, really. McCormick and Company defines a lot as a full production run per process order. So you got a customer order, you run for that Costco order or that Safeway order, that full run. Does it have to be defined that way? No, it could be a truckload, a pallet, or it could be defined in any number of ways, but the government inspectors tend to think on the smaller side. So if you try to over define and make it too big to give yourself some cushion, well, those 5 pallets were a little underweight, but these 6 pallets were a little overweight. You got to be careful. You got to know the regulations, but don't worry about how a lot of product is specifically defined. So weight control charts, we've seen those. That's paper documentation that has largely been taken over by apps and by automated machinery like Datamite, which automatically plots the material. You still have to have somebody go around, take the samples, and do the weights. Now, the weight recording device, the balance or scale that is used to measure these is connected to Datamite. So you put the bottle on, you hit a button, and you don't even have to write it down or type it in. It automatically is sending that weight into the machine. It automatically generates your averages, your ranges, and plots it. There's also something called the check weigher, which is a safety net. And the check weigher is a scale or balance that is a high-speed device. And as the bottles are finished packing, they go past these the scale at a very high speed. And if that scale recognizes that you've got an underweight, now it says low and high. I think at McCormick it was just the low that they were mostly concerned about. But if you have a super overfilled bottle, it could also kick it off as well. So anything that has way too much stuff in it or way too little, it'll kick it off. There's a little arm, so this goes by the scale, and it's based on a timing. So if it goes by the scale and it's traveling at a certain rate of speed, that arm will go slap and knock it off of the line as it exits the scale to make sure that it's a safety net from accidentally getting underweight bottles into the boxes or pallets that are going to the customer. So check weigher is another tool to help avoid sending defectively filled product to the customer. Remember that our goal is to continuously produce materials within legal limits of the label weight requirements while minimizing overfilled units. Weight control charts and Datamite system, along with our check weighers, are the best tools we have to help ensure that we meet customer expectations while sustaining a profitable business. Now, I know places that have been using weight control charts up until quite recently, but because apps are available, the idea of running around with a clipboard is getting less and less common. It's only very small operations doing things for niche markets, restaurants, things like that, that might still manually do their weight control chart types of SPC. Most of them have gone to tablets where they can punch things in very quickly into a very simplistic app or a much more sophisticated system like Datamite, which integrates into your processing lines. In summary, by utilizing SPC and following the proper corrective actions for out of control situations, we will help McCormick avoid legal fines, unhappy customers, and unnecessary rework costs. So what happens if you run and you have a MAV violation? You either have to throw out product or open all those bottles, dump them back into a container, put the bottles back on the line, rerun and refill them, or maybe throw the bottles out but save the oregano in the product. It depends on what you do, but that's a lot of work. And reworked product going through the process twice, maybe it packed down, it broke down a little bit. Maybe now you're not going to meet the fill line. So you're not going to make it to 2/3 full or whatever the refill or the fill line, visual fill line requirements are for that bottle. You don't want your customer feeling cheated. And when you do rework, sometimes it doesn't fill as well. Now you got more problems. You'd never want to do rework. Do it right the first time. So that is it for statistical process control.